Have you ever heard about quantum computers? If you did, you might have been told that quantum computers are amazing machines that will bring upon a revolution, and that they are way stronger than the most powerful machines in the whole world. If you haven't heard about them, it's okay, because now you will understand everything you need to know about these apparently revolutionary machines.
Of course, it is correct to say that quantum computers will be disruptive in the future, and they will mean a giant leap in the history of technology. However, if you think that in 20 years' time you will be enjoying the power of one of these machines to play Battlefield 5 at 240 FPS, you are really wrong. And in this video we are going to explain why. Anyway, we cannot really understand quantum technology if we don't talk about classical computers before. So let's make some things clear.
Firstly, in a classical computer, every file that you store is made up of bits. One bit is the smallest piece of information that can be stored, and it can be set to a 0 or a 1. This is what we talk about when we say that computers work on a binary system. Every image, every password, every text can be translated to bits, to zeros and ones. When a movie occupies 1 GB of information, it means that it can be represented with 8 billion bits.
Secondly, computers are based on really tiny elements called transistors. These could be interpreted as little switches that block or open the way for electricity, which is electrons moving from one place to another. Have this in mind because it is very important. In the same way as bits, a transistor can be in two different states. State 1 if it allows electrons to move, or state 0 in which it blocks the way for electricity. Transistors can be combined to build logic gates that perform logical operations, and logic gates are combined to create modules that can add two numbers together. Basically, the processor of your computer is made up of millions of these modules. Yes, the computer you use to play your favorite games is made up of modules that just add two numbers together.
Before the transistor, the computers were based on vacuum tubes, which were a larger version of the transistor. They had the same function, but they were too big, and that's why the first computers were as large as a living room. So scientists at Bell Labs invented the transistor. The transistor made computers smaller and allowed engineers to build much faster machines. Until now, scientists and computer engineers have been trying to make the transistor smaller, so that we can increase the power of the processors by adding more of them every time. In fact, Moore's law tells us that the number of transistors in a microprocessor doubles every 2 years. But this seems to be over. We have reached a physical limit, because right now the transistor size is about 10 nanometers, and this is the size of a few atoms.
This means that we will probably not be able to make them significantly smaller in the future, because making them smaller could lead to conflicts between computation and the laws of physics. This limit restricts our processing capacity. If we can't make transistors smaller, we can't increase the number of transistors in a CPU. So we won't be able to make classical computers much more powerful in the next 20 years. This sounds terrible, and if you care about the future of humanity, you may be wondering if there is something to do about this. And here is where quantum computers show up. Do you remember when we talked about how classical computers work with bits? We said that every operation was reduced to strings of zeros and ones. Well, quantum computers work on a similar way. However, instead of using bits, quantum computers use qubits. Qubits are different from bits because although they can also be set to 0 or 1, they can also be set to any proportion of both states at the same time.
What?
Yes, and we will explain this counterintuitive idea just now. Qubits represent the state of any two-level quantum system. For example, you can use a property of electrons called spin, which, to our purpose, can be explained as its energy level. This property can be illustrated as an arrow pointing up or down. We can say that spin down would be represented as a 1 in the state of the qubit, and spin up would be represented as a 0. Electrons don't have a defined spin until you do a measurement. So before you check whether the spin of the electron is up or down, the qubit value is in a superposition of both states. It has some probability of being in state 1 and some probability of being in state 0.
This property is called superposition, and we will see why the fact of having qubits whose state is not determined is the main advantage of quantum computers. For example, here we have 2 bits. This combination of bits can be set to any of these 4 states, but it can be only set to one of them at the time. However, quantum bits can be in all of those states at once until you do the measurement, and this is extremely powerful. We can imagine the following situation. Let's say that I want to crack a 4-bit password. In a classical computer, it should try any combination of inputs 000, 001, 0010, and so on. This can take up a long time, considering that in the worst case, I would need to enter 16 different passwords. In a quantum computer, we could introduce a superposition of 4 qubits that are in 16 different states at the time, of which one of them is correct. And by using some techniques, I can discard the wrong answers and crack the password in only one try. And we're not done talking about quantum computers' new features. There is another important property that is called entanglement. Basically, this property consists on the fact that we can have 2 qubits that are unconditionally connected, and when you change the state of one of them, you immediately change the state of the other. So if I have these 2 electrons entangled and I measure the state of the first one to be 1, I know that the other will be observed to be 0, and this property can be harnessed to optimize programs that in a normal computer could take years to run.
Quantum gates are another interesting concept. In classical computers, we have basic operators called logic gates. These gates return a specific output for a set of inputs. For example, the AND gate returns an output of 1 if both inputs are equal to 1. One set of inputs leads to one output, as simple as that. To obtain every different output, we have to run the circuit many times as we change the inputs. On the other hand, in quantum computers, the input is a superposition of states. Logic gates are replaced by quantum gates, which can modify the probability of measuring one certain output. Basically, instead of running the circuit many times, on a quantum computer you can run this algorithm introducing all the possible inputs at the same time, so you can obtain the correct output much faster. Imagine that we need to calculate the best path from one place to another. An everyday computer should try every possible way, one by one. Instead, a quantum computer would accelerate this process exponentially by comparing all the possible paths at the same time.
There are lots of examples that are similar to this last one. Quantum computers could really help scientists to simulate complex molecular clusters. They will also be incredibly fast to decrypt secret information and to sort optimization problems, such as scheduling the departures and arrivals of giant airports. You could also dream about a super quantum computer managing thousands of self-driving cars to organize traffic in the most efficient way. In the end, it's all about believing in innovation. This is a picture of one of the first computers in history, and this is one of a quantum computer today. A great way to show that history repeats itself. 40 years ago, we couldn't have imagined that computers could be commercialized, and now every one of us has a smartphone in their pockets. Let's dream about what the future holds and contribute our grain of sand if it is possible, because that is how science is made.